thanks. That's good. So hello everyone, and thanks for joining in for today's webinar. Today, this is the continuation of our webinar series, and in the first webinar that we had a month ago, we covered offline condition monitoring, or our motor condition tester unit. And today we are going to focus on the online condition monitoring, where we will talk about how we can offer valuable information for rotating equipment, for the critical rotating equipment in the industry, where we provide a comprehensive approach with our model-based voltage and current analysis technology. So before we start, for the attendees who are new to our webinars, just a little bit history of the company quickly. Artesis has been around for 20 plus years, and the initial applications of the Artesis technology goes back to late 1980s, where this model-based current and voltage system identification technique was initially started at NASA, and the initial applications of this technology were applied to helicopter motors and space shuttle engines. And later on, this technology was commercialized and applied to industrial applications for induction motors or any rotating equipment that is driven by induction motor. And before we go into the technical details, what this technology will provide you, basically, we can summarize this in 5 different steps or features. First of all, the goal of this technology is to simplify condition monitoring and provide the users actionable information, whereby eliminating the need of detailed data analysis. So much of the data analysis is being handled by the software. So the second thing, and as you can see here, you get the bar graph representation of different faults, which we will elaborate later on. Second thing is the comprehensive fault coverage. So this condition monitoring technique will give you a more global view of what's going on your rotating equipment, covering mechanical, electrical, and process faults altogether. And that's, of course, much more valuable going in there with local different tools to check in them. So, and it's covering, again, more fault types here. The fault detection accuracy is pretty high, which we will again delve in more later on. Another feature that this technology offers is that it can do power monitoring and also provide the energy efficiency effects of the faults. So, and last but not least is by using this technology, you can actually integrate this into your central monitoring platforms, where the integration can be done via OPC. Now, we do offer the AMT Pro, e-MCM, and e-PCM, and today we are going to talk about the e-MCM, where this product is for the online condition monitoring of critical rotating equipment. And before, we are going to talk about how this technology works, what's the technology behind it, and how it can actually prove to be valuable for your rotating assets. Now, this model-based fault detection technology basically creates a model of your equipment or rotating equipment that, of course, includes the motor, the drivetrain, and the driven equipment altogether. So that's the real value of this technology, where it can monitor the whole rotating system. Now, here with our system identification or model creation, what we are doing is we are taking the voltage as an input, and then, of course, the voltage goes through the motor, which drives and rotates, and it creates a current output. So And in a perfect condition, when you supply a voltage at certain frequencies, the output current signal that you're getting actually should be free of any distortions or any harmonics, but in reality you will get some level of harmonics at different levels. So, and here when you have that, which is not present on the supply voltage, that means the mechanical behavior of the motor is causing these distortions on your current waveform. So now here, what our technology does and the model-based system identification we're doing here is that it actually learns how this physical asset is behaving under different conditions, under different loads. And we have this model creation time, which varies from 7 days to 10 days. And once this digital twin is created, it behaves exactly as the motor behaves. And then, of course, after this learn period is completed, we are constantly monitoring the actual equipment, and depending of the deviations or developing or incipient faults, you will see these additional peaks on different frequencies. So, of course, depending of those frequencies and the amplitudes, you will have this residual current waveform distortions. So what this means here, our voltage supply is the same, and our learn model is here, and we are constantly monitoring, and we are taking the difference between the two. So there are some additional frequencies, these distortions we are seeing here. So those must have come from the mechanical changes in the motor behavior. So, and we are analyzing this in the power spectral density, and we amplify them. And we're looking at the frequencies here and the amplitudes, and these will tell us what type of fault this is, and also what severity or how severe these faults are. Now, another feature that this approach provides to the users is that it is capable of distinguishing the electrical issues from the mechanical faults. What I mean by that is here, if you look at this part, and if you have harmonics on your supply voltage, which is not a clean signal to the motor itself here, that can cause, for instance, if you have a voltage unbalance on your supply voltage or your compensation is not right, you will see a dirty power here, which can then vibrate the motor itself, or in the long run, it can cause stutter issues or other issues on the motor itself. So with a purely mechanical approach, you won't be able to identify this unless you look at the input power. So here, the e-MCM, or this model-based fault detection technology, since it's also looking at the input voltage and input power, you can see here the same distortions are present here, which means this is not a mechanical fault but an electrical one. So that's how we can distinguish between two different fault or root cause of the faults. And furthermore, of course, by using the voltage, we can create this cause and effect relation, and also create these different operational conditions of motors. And whenever a new process is present in the system, we can see and say that this process has not been learned. It may be an issue, so then the user should check whether the load changes that are not present before are an intentional change or actually an issue on the process itself. So now, of course, the fundamental of this technology comes the mechanical faults propagating the faults into the air gap between the rotor and stator. So in a normal operational condition of the rotating equipment, What happens here is that you have a uniform electromagnetic field between the rotor and stator. But when that uniformity is distorted because of developing fault, this could be a bearing fault, this could be an unbalance, you can have a loose belt. So any type of mechanical faults on the motor itself, the drivetrain, and the driven equipment will distort this air gap. So when that happens, you will shift or distort this air gap, and that will cause dynamic or static eccentricity, which will then, of course, distort the current waveform at certain frequencies, dependent of the fault type and dependent of the rotating speed of the components in the drivetrain or the driven equipment or in the motor. Now, I mentioned that this technology for online condition monitoring requires 7 to 10 days learning time or model creation or digital twin creation of the rotating system. The reason for that is it needs to learn different operational conditions by looking at the power factor, the frequency, and the gain of the system, which takes into the current and voltage. And what it does here, it creates different operational clusters. So each cluster will contain its own set of learn model. And when in monitor mode, then the e-MCM will constantly compare the monitoring information with the closest cluster that it created that the thresholds for. So when there is a new operational condition presented into the system will warn the user again that this particular load condition has not been there before. An example here, say monitoring a cooling tower fan in winter and in summer, they have different operational conditions and different speeds or load levels. So, and if you take this unit if you commission this let's say in summer, and when the winter comes, the behavior of those cooling tower fans will change, and the system will then notify you that the behavior of these fans have changed. So you should check whether there's an issue or not. If it's not an issue, and if it's a seasonal change or intentional change on the system behavior, you can then update this model inside by just updating the software, and then it will create additional clusters for that particular condition. So that way you always ensure that all conditions are learned, and you're monitoring and you're constantly comparing the actual process with what has been learned. And if you see any deviation in between, then that will yield early indications about an incipient fault. So now, and of course, this is the e-MCM product that we have. And as you can see here, a summary of its features provides online condition monitoring, of course, early fault detection, most importantly, automated fault diagnosis, remote monitoring, comprehensive fault coverage, energy efficiency effects of the faults, and also being the only viable solution out there for hard-to-reach applications, submersible pumps, or again, cooling tower fans, or hard-to-reach applications. So starting with the effortless monitoring, what this would mean for the users, basically, again, it eliminates a lot of manual data analysis. So it monitors the rotating equipment for you whenever there is an issue or an issue starts to develop, whether it's mechanical or electrical. You will see this management view screen where the faulty equipment will give you a traffic light warning, and where you can actually see and take action further. So if you see green lights on the screen, that means those motors are running fine. You don't have to intervene or take any actions on it. So which will make the job of the maintenance personnel a lot easier. Now, when you see an issue, so you, of course, you want to dive deeper and see what's going on. And this is really where this technology excels by giving you this automated fault diagnosis information. So when you have an issue, you can look at here and then see these bar graphs giving you the indication where the faults are. So for instance, we have here a loose foundation. So there was a foundation looseness on this equipment, but it was already there when the equipment was first commissioned and learned. So, and the good thing about this bar graphs, it gives you the trend information as well. As you can see here, you have 2 bar graphs per failure type. So basically, the light blue indicates the initial learning results, and the second one is showing you the most recent condition. So the difference between the two will tell you whether this problem is getting worse or you have fixed the issue and it went down back to normal levels. So we have foundation looseness, unbalance, misalignments, transmission, which contains, of course, gearbox, belt, or if you have coupling, those types of failures, bearing faults, rotor, stator, and internal, external electrical faults. So, and furthermore, if there's a fault present, of course, it will list you the energy efficiency effects of those faults. But on top of that, you will be able to monitor the power consumption, active, reactive power usage, or all electrical parameters, and you will be able to trend them, including voltage current RMS values, voltage current unbalance values, which can be an indication of mechanical fault in the rotor or stator, and harmonics, and you will see frequency, of course, as well. Now, for 1 second here, and of course, if you have 1 second, apologies here. If you have to go deeper to analyze the faults, we have spectrum analysis, which I cannot see on my presentation. We have the spectrum analysis and trend analysis where you can dive deeper, which we will cover with some of the case studies at the end of the presentation that I have. So we'll come back to that later. But just to quickly go over how this whole system is installed. Basically, for every machine out there, you will need one of these e-MCMs. And then on the local level, you will install these into the motor control panels or motor control rooms. And from there, you have to communicate to a server through the switch in the substations or motor control rooms. Then you can either use on-premise solution or the cloud solution that we have. The cloud you can, of course, access through web browsers. So if you want to keep in-house and on-premise, we have the on-premise software, and you can keep everything locally. And if you want to integrate that into your own OPC platform or to your own monitoring platform, you can do so via OPC integration there. And some snapshots from the cloud-based software that we have. And of course, with the cloud, you can also keep the cloud to yourself. If you have a virtual server, we will provide the software for the cloud as well. And you can access it, of course, online remotely via different web browsers or mobile tools. And if you do not have a wired installation in your premises, sometimes some pump stations are not connected to the Ethernet or they don't have wired connection. So you can use 4G routers directly to communicate to the cloud. So that would be another option. So basically, we do offer this flexible different communication or software platforms for every need. So That way we ensure that you can monitor your assets, whether on-premise or on cloud. Now, there are some limitations to this technology in terms of the applications that it can be applied to. And these are, the equipment needs to be 3-phase AC motors. We cannot monitor DC motors or servo motors, so that is important. However, there's no power or voltage limitation, so we can monitor low voltage or medium voltage systems. And whether the system is driven by a VFD, it's a variable speed motor or generator, there's no issue there. It can be monitored. And also dependent of the fault types and alarms, this will give you electrical process or mechanical faults in different categories, where, as you can see here, if you have a watch line, that means you have an issue as in the incoming power. If it's the loads, you have an issue at the output, which is your process. And mechanical faults have 2 severities, examine 1 and examine 2, depending on the severity level of the issue. And so monitoring via MCC panel here, it gives you the ability to monitor these hard to reach or inaccessible applications, examples, submersible pumps, cooling tower fan, borehole pumps, or ATEX zones. So since it does sit on the MCC panel, you do not have to install any sensor on your rotating equipment. You don't need to access it. Basically, the installation here, as you can see, is pretty simple and straightforward and shouldn't take more than 10 to 15 minutes. So you connect your voltage cables, then current transformers for the current, and you have the Ethernet connection basically to communicate to a server, whether you want to use a local server or a cloud server. That's how you communicate. Yeah, this is this presentation I lost previously. So with the spectrum analysis, you can do the advanced analysis. I mentioned in the beginning that we do simplify condition monitoring, but we also have these advanced tools for advanced users who want to dive deeper to find out the root cause of the issues. So the spectrum analysis is similar to vibration analysis. Depending on the faults, you have faults appearing at certain frequencies. So, and for instance, if you were to have an unbalanced issue, you would see a one-time RPM of the rotational speed plus and minus of line frequencies. So, and I think a lot of the vibration people can be easily acquainted with this approach here and analyze the spectrum if needed. Furthermore, of course, the trend analysis will give you the trending of the historical data and the trending or the pace of a developing fault, so that you can have an estimation that you have how much time you have left to the failure point. So, and also you will be able to cross-check between the mechanical and electrical faults by looking at the signal frequency or voltage or current levels, and then relate them to a mechanical faults or stutter issues or rotor issues. So these two tools will be very valuable for advanced analysis. We have these tools available both on the on-premise software and on the cloud software. So that is important. Now we have some quick case studies here. So an example, this was any gearbox issue that we have detected with the e-MCM. This was a couple of years back, and this was actually a proof of concept kind of monitoring that we had. As you can see here, the data that we have came right after the learn period, which was approximately 10 days. And the customer already was suspecting, or the user was suspecting, that they had a gearbox issue. We physically went to the site. We were hearing that some unusual noise the gearbox system was making on the conveyors. and this was a car manufacturing plant, so you can understand the criticality of this asset, because on the conveyor system, if gearbox were to fail, then they would have lost $250,000 per hour, because the production will be interrupted and stopped until they fix the issue and get back to normal. So after that first initial learn period, what happened here is that we were able to see that there was a transmission which was automatically diagnosed here. The transmission was a gearbox. So this was a reduction gearbox, 90-degree angle. And as we can see here, those issues these were 17 hertz plus and minus the line frequency, which was 60 hertz. This was in the United States. So the running speed of 70 hertz would be equal to 1020 RPM, which was the rotating speed in the gearbox. So that was the issue that we detected. And of course, the user wanted to verify this with vibration analysis, which they did. They used vibration, and they already had a online vibration monitoring. So they verified our findings with the vibration as well. So, and this is, of course, to show that this system is very valuable by monitoring the whole asset. You know, it's not only monitoring the motor itself, but you can see what's going on your transmission, which is very, very valuable for these types of assets. Another case we have is it was an external electrical issue. And as you can see here, after we were monitoring this equipment, it already had some issue, transmission and bearing. The user was aware of this. But what was new here is that this external electrical went up very quickly, significantly, and they were concerned about what's going on here. And then with the analysis here, with the trend analysis, they were able to see it was an external connection issue. So they went and checked connections were loose. So, and then when they fixed that, it went back down to normal, as you can see here, very quickly. Another case here is a bearing fault. With these type of faults, of course, the trend analysis, and as you can see here, the management view proves to be very easy to use, because you can see here it turned into red. When you click on it, it will directly take you into this trend analysis of that particular fault, which was a bearing fault here. And when they actually replaced the bearing fault went back down to normal levels here. Another one here is a fan with a belt driven system. You can see here, this was again at these normal levels, and it started to go up and up and up, and the belt issue was getting more serious. So the user eventually took action and fixed the issue, and then the belt went back to normal levels here. And finally, we have here a winding failure. This was an interesting case because actually the equipment failed and it burned. But when the user, got in touch with us and asked about this, they realized that the system was warning them already for quite a long time, and it was given an examine one alarm, which sounded, it was a red alarm basically. So, but they didn't take action on time, so it actually failed. So the equipment got burned, and then when they sent this motor for rewinding, at first try, when they did the rewinding and got back got the motor back and make it operational, they realized that the currents and the active power under the same load was higher. So there was something wrong here, and we consulted. And we gave them the recommendation to check the windings again, and then they sent back to motor again for another rewinding. This time it was correctly implemented, and then the motor's active and current values went back to the normal levels, and then so this was kind of a double check of whether the maintenance action was done properly or not, which wasn't in this case, but we were able to detect that, and then they rewinded the motor again, and it was back to normal. And the final case we have here is, this is another fan. This had a couple of belts. One of them ruptured, and as you can see here, it went up significantly. And this red you see here, it's actually a threshold. When you exceed this, you will get an alarm, which was the case here. And after that, replace that belt, it went back to normal levels. So yeah, this is pretty much you know, the presentation here, and try to cover different fault types, electrical, mechanical issues. So if you have questions now, I will try to answer them. I think we will see the questions on the chat box, so I will read them and answer them.
Thank you so much, Tumen. Can you close your screen share? And yes. And I am open. Now I am open the chat.
Okay, I already started to see the questions, so I see that what kind of faults can be detected in case of submersible pump application. We actually have different types of faults, including bearings or imbalance, or even you know, pump impeller issue detections for submersible pumps. So the submersible pumps are no different than other pumps or you know, other applications that we're monitoring. So basically, there are three components for us: the motor itself, the drivetrain, and the driven equipment. So when there is a problem here, we will be able to detect that. How do we catch a problem with the voltage efficiency chart? Didn't understand that greatly, kind of about mechanical fault detection. So okay, let me just go quickly. So the mechanical fault detection, this was a question from Rami. So basically, each type of mechanical fault will distort the air gap between the motor and between the rotor and stator, so that will translate into fault frequencies at the current waveform, and that's how we are able to detect mechanical faults. Recording will be available. Yes. Can we take data to the other clouds? We do not have API, but we do offer, again, OPC or SQL integration. You can take it to other platforms of your choice. Can we early detect lack or cover lubrication issues? Yes, you can actually detect lubrication issues. We have some cases. Of course, that will show itself as bearing faults. It will be detected that you have the bearing issue, and you can actually do detailed bearing analysis when you enter the bearing specs into the spectrum. You can look at the inner cage, inner race or outer race, or ball spin frequencies. So, and if you look at deeper, you can see whether it's actually because of the lubrication or not. And so another question we have here is, what is the difference? What is the difference between AMT Pro and AMC? AMT Pro is a portable unit which does and detects issue, a 7-minute test, and detects the issues on semi-critical equipments. Basically, it takes a snapshot, doesn't give you basically the historical or continuous monitoring, historical trends or continuous monitoring. So, and it is suitable for semi-critical machinery, whereas the e-MCM is good for critical motors where you require constant or continuous monitoring. So that's the difference between the two. Can we take raw data directly? Yes, you can take the raw data directly to other dashboards via, again, OPC, or you can get the SQL tables from us and integrate it into your own dashboards. What ambient temperature range the device operates? It's -10 plus 50 Celsius. And since actually this is already always installed into an MCC panel where other electronic devices are operated, so it should not be an issue. With the analysis tools interface, would we be able to view waveforms and spectrum? Yes, the spectrum is already there. You can manually capture waveforms and look at the waveform if you like as well. So that is also available in the software. So another question here regarding the installation issues specifically for high voltage motors, is it possible to use the previously installed CTs and VTs? That is a great question, actually. I forgot to mention about this. Yes, actually, we do require and use the previously installed existing CTs and PTs for the medium or high voltage motors. And we basically, what we do here is we tap into the secondary side of the PTs and CTs. The e-MCM can be connected directly up to 690 volt to the motors. Anything above 690 volt would require a VT and CT, and we use those to monitor. Difference between the three products, again, e-MCM and e-PCM. e-MCM is for motors, e-PCM for generators and wind turbines, and AMT Pro is the portable diagnostic tester, which does a quick 7-minute test and get a snapshot for you. So this device can predict a failure in the motor. Yes, one of the fail modes that we can detect on the bar graphs, as you have seen, is rotor issues. So if you have a rotor bar or broken rotor bars, this can see and detect the rotor issues as well. This could also detect a failure in wanted rotor slip ring motor. Yes. Is it possible to use this system for rotating type machines like filler machines with AC, which are driven? Yes. Filler machines which are driven by AC motors, yes. The only limitation here would be the speed. So if the speed is between 20 hertz to 120 hertz, it can be monitored by the system. How often the spectrum updates? So that's a good question. The spectrum is actually updated every 1.5 minutes, and that's the default value. So what the system does, it actually captures a waveform every iteration. Each iteration is 90 seconds, and the waveform length is 6 seconds at 2.5 kilohertz. So that is constantly going on. But however, the spectrums that are captured is processed internally in the device, but the result of those spectrums, I think that's what you're referring to with this question, is how often it is updated there. At default is every 10 hours, and the trend data is every 15 minutes. The reason for that is we try to optimize the database storage because we do use an SQL database. But if you want, you can actually make those, one iteration, which is equal to 1.5 minutes. So you can update the spectrums every 1.5 minutes, but that will unnecessarily fill the SQL. There's a question about the SAM4 solution. Yes, we know, of course, it's a new, we founded company in the predictive maintenance I think one of the biggest differences between Artesis and SEM4 is that they do not have this model-based approach that we have and do not create a digital twin, but more importantly, they require a longer period of time to learn an equipment and don't have an automated fault diagnosis. And another one is that Artesis actually has created and accumulated a motor fault database where at the end of the learn period, we actually detect the existing faults by referring to this proprietary database that we have. So that's critical, because if you learn a motor and you say that you create a digital twin of that particular motor, but that motor, when it's already faulty or when it already has some issues, and if that's your starting point without knowing that you know there are some faults present in it, then how can you be effective? So I think I would say one of the biggest differences is that with our approach, we are able to detect existing issues and notify the user, and that will be the initial starting point. And from then on, of course, we constantly compare the equipment's condition with the learned condition that we have. So that these are the major differences. Another question here is, so on the stutter, I think wedges losing. So we are not able to say that this is a stutter wedge issue. However, we can say that it is a stutter problem. So you may need to follow up with other tools to go dive deeper on that stutter issue. This will give you the first indication that your stutter has issues. So I think this is how you should look at this technology. So another question is, in case a 6.6 kilovolt, can we connect current voltage from existing? Yes, you can connect CTs and PTs as long as these CTs are the measurement types, not the protection types. The accuracy there is important. So if it's protection type CTs, they are not very accurate. So that would be the limitation there. Can the e-MCM detect the overheat of the motor connection termination? Will mechanical affect overheat of the motor electrical termination? Yeah, we have actually cases, you know, if there is overheat, it will show itself as an external fault, and also it will create some anomalies on the voltage and current unbalance values. Again, we won't be able to say it's an overheat there, but you will be notified or see on the trends that something is externally going on there. Does the VFDs affect the accuracy of the results of data? That is another question. It's a good question that we get constantly. No, the VFD, we can monitor VFDs with the same accuracy we monitor line-driven fixed-speed motors. And however, with the VFDs, the learn period is different than the line, which is 10 hours, and after that, there is another 10 days of improvement. That's the only difference, but it doesn't affect the accuracy. And since we have this clustering algorithm, so we create hundreds of clusters for different speeds, different load levels of the motor. Would we schedule the frequency of data collection? Yes, you can actually change the settings on the software. Again, that was a previously asked question, so Pravin asks this. Yes, you can change that, and you can make it as short or as low as 1.5 minutes. In case of a motor overhauls, in case of a major overhaul or rewinding of the motor, you have to relearn the motor. So that's because that changes the characteristics and the behavior of the motor. It needs to be relearned. If the motor is on and off periodically, such as chiller, yes. So basically the question here is that if the motor is not constantly running and running on and off periodically, it won't affect the MCM's ability to learn it. However, it will affect the duration. So it will take longer. It will start learning or continue learning when it's on. If it's off, it will pause and wait and resume when it's on again. So it's just gonna take, how about dealership in India? So that's going to be taken care of after webinar. All right, Natalie, thank you. So I think I pretty much covered all the questions so far. So, and there don't seem to be any other questions. Thank you very much, everyone, again, for joining in. If there's no more questions, I think we will close this session. However, for next month, on these 2 webinars we did so far, is we touched on the surface of these technologies, but moving forward, the next month we will go and have detailed cases and explanations of how this actually is working and how we can do the spectrum analysis and all that. So thanks again. Thank you, everyone. And hopefully we will see you guys on the next webinar. So thanks.